Kia ora. Today we're going to look at two new ideas, similarity and diagonalization. This is a very general technique which can allow you to make sense of very large and complicated matrices and to simplify them dramatically. Before I write down the formula for matrix similarity, I'll just motivate it with one of the applications, which is to simplifying linear transformations. So suppose we've got a linear transformation T of x, which is equal in matrix vector form is written matrix A times vector x. And let's just write that as a transformation where old x maps to new x prime. Input vector x, output vector x prime. So x prime equals ax. And now consider making a change of variables so that the new variable y is equal to some matrix P inverse times x. Or to put it another way, x equals py. If the matrix P is invertible, which is assumed because I'm writing P inverse, then I can go back and forth between the old variables x and the new variables y. How does the linear transformation look in the new variables y? Well, y prime, the output y, is going to be P inverse times x prime. That's P inverse times ax. But x is py, so that's y prime equals P inverse a py. So the matrix of the linear transformation in the new variables y is P inverse AP. That means that the matrices A and P inverse AP actually represent the same linear transformation, just written in different variables. It's very similar to a change of units in physics. If you measure a length and the length is 5, it's very important to know whether that's 5 centimeters or 5 inches or 5 kilometers. If you change the units, the numbers would change. With linear transformations, if you change the variables, here I've changed from x to y, then the matrix of the linear transformation would change. There's another thing. I could start with the matrix A, and then I could try and choose the matrix P to make the best possible change of variables, one that would simplify that matrix A as much as possible. And it turns out that by the end of this lesson, we will know how to do that. So this leads to the definition of when two matrices are similar. The matrix A is similar to the matrix B if there exists an invertible matrix P such that P inverse AP equals B. Matrix similarity. So there's an obvious question here, which is given two matrices A and B of the same size, two square matrices, how would you tell if they're similar or not? Well, that turns out to be a little bit difficult. But there is one case that I can give a complete and fairly simple answer to, which is when is a matrix A similar to a diagonal matrix? The diagonal matrices, they're about as simple as you can get. So we say that a matrix A is diagonalizable if it is similar to a diagonal matrix D. So if there exists an invertible matrix P such that P inverse AP equals D. Well, that was the definition. But that leads to a question, given a matrix A, when is it diagonalizable? How do you tell when it's diagonalizable, or if it isn't? Are all matrices diagonalizable? Turns out they're not. And if it is diagonalizable, how do you find the P and the D? So we can give a very complete and simple answer to that question using eigenvalues and eigenvectors. The theorem says that a matrix A is diagonalizable if and only if it has n linearly independent eigenvectors. I'll call them P1 up to Pn, and they must form the columns of the matrix P. And the diagonal matrix D must contain the eigenvalues on the diagonal in the same order as the eigenvectors. So it's a complete description. If you have n linearly independent eigenvectors, then your matrix is diagonalizable and you know the transformation that diagonalizes it. If it doesn't have n linearly independent eigenvalues, then it's not diagonalizable. It's a complete answer. Now this theorem is so important that we're going to prove it right now. This theorem is one of those if and only if theorems. So that says the matrix is diagonalizable if it has n linearly independent eigenvectors, but also that's the only way it can be diagonalizable. So we have to do two cases, the if and the only if case. So first off, let's suppose that A is diagonalizable, so there does exist such a matrix P and such a diagonal matrix D. And let P1 up to Pn be the columns of matrix P, and let the numbers A1 up to An be the diagonal entries of the matrix D. So we're given that P inverse AP equals D. Now I will show that actually those numbers AI were in fact the eigenvalues of A, and those vectors Pi were in fact the eigenvectors. So we're given P inverse AP equals D. I'll do some matrix algebra. I'll multiply both sides of that equation on the left by matrix P. P inverse AP equals PD. PP inverse cancels because PP inverse is the identity matrix. That gives me AP equals PD. Now I'm going to write out that matrix equation in columns. That gives me A times matrix P1 up to Pn is equal to P1 up to Pn times this diagonal matrix. Multiply out the right hand side, you get its columns are A1 P1 up to AN Pn. Write down every column of that matrix equation and you get API equals little ai pi. Well, that's just the eigenvalue equation, AX equals lambda x. That means the only way that equation can hold is if AI is an eigenvalue and PI is its eigenvector. What about the linear independence part? Well, we were given that the matrix P was invertible. That means its columns are a set of linearly independent vectors. The columns were the eigenvectors. That means A has n linearly independent eigenvectors. How about the other way around? This time we're not given P inverse AP equals D, but we are given that A has n linearly independent eigenvectors. So in that case, we will just stack those eigenvectors into the columns of P, and we'll choose D to be the diagonal matrix with the eigenvalues on the diagonal, and we'll basically now run that calculation in reverse. We're given API equals lambda I pi. That gives AP equals PD, or P inverse AP equals D. And we're also given that the PI's are linearly independent. That means that the matrix P is invertible. So we've done both directions. It's a very powerful theorem, and the nice thing is to use that theorem to both tell if a matrix is diagonalizable and to diagonalize the matrix to find P and D. You don't need to do any work whatsoever once you have found the eigenvalues and eigenvectors. Let's see that in an example. I'll do the matrix I did in the last lesson. So matrix A is 2, 0, 3, 2, 0, 3, 3, 2, 0. We found the eigenvalues last time. They were 0, negative 3, and 5. And we found the eigenvectors. The eigenvector for 0 was minus 6, 9, 4. The eigenvector for eigenvalue negative 3 was negative 3, negative 3, 5. The eigenvector for eigenvalue 5 was 1, 1, 1. So I just stack those into the columns of P. Those three vectors are linearly independent, and we're done. We've diagonalized the matrix. What could go wrong? Well, I did another matrix in the last lesson which illustrates what can go wrong. That was this matrix, minus 1, 0, 2, 0, 1, 2, 0, 0, 0, 0, 1. That matrix is not diagonalizable. That was the matrix which had a double eigenvalue 1 with only one eigenvector. So where could I possibly get three linearly independent eigenvectors? I've got one eigenvector that goes with the eigenvalue negative 1. I've only got one eigenvector that goes with the eigenvalue 1. There's no way I can get a third one. So this is the bad case. These are the matrices that cannot be diagonalized. They're the ones where you have repeated eigenvalues with not enough eigenvectors, where the dimension of the eigenspace is less than the number of times that eigenvalue is repeated. Let's state that as a theorem. Matrix A is diagonalizable if and only if the algebraic multiplicity of eigenvalue lambda I is equal to the geometric multiplicity of eigenvalue lambda I for all I. And that holds, for example, if all the eigenvalues are distinct, because then they all have algebraic multiplicity 1. Everyone must have an eigenvector. And in the textbook, it's proved that the eigenvectors corresponding to distinct eigenvalues are linearly independent. I won't prove that here. I'll refer you to the textbook. Let's do a couple of applications. The first one is the one I mentioned earlier, to simplifying linear transformations by doing a change of variables. We've seen that if matrix A is diagonalizable, then the linear transformation x maps to x prime, where x prime equals ax, can be transformed into y prime equals dy, where d is diagonal. Write down the components of that equation, you get yi prime equals lambda I yi. Well, that's just a scaling transformation. That's just like take the number yi and multiply it by lambda I. It's like a doubling or a tripling. So these diagonalizable matrices, they correspond to very simple linear transformations, and this is the main way of understanding what is the structure of a linear transformation. The second application will be to computing powers of a matrix, which is not just an important algebraic operation, but it's important in applications too, which we'll see next week. So we're given a diagonalizable matrix. So we're given that P inverse AP equals D, and we'd like to calculate the powers of the matrix. Now you could just work out A squared or A cubed by multiplying out the matrix. But what about A to the power n, where n is a variable? You can't do that just by repeated multiplication. You need a formula as a function of n. So here we go. Let's simplify that equation by making A the subject of the equation. That means I'm going to multiply on the left by matrix P and on the right by matrix P inverse. Then I will get A equals P D P inverse. That means A to the power n is P D P inverse, P D P inverse, P D P inverse n times. Now notice that all of the P inverse P's in the interior all cancel because P inverse times P is the identity matrix. So this simplifies to P d to the n P inverse. But what about d to the n? That's very simple. Diagonal matrix raised to a power n, you just take the nth power of all of the diagonal entries and you're done. This will give us a formula for the nth power for any matrix that can be diagonalized. Let's just do a very simple example. I'll take the matrix I had a couple of lessons ago, 1, 2, 2, 1. Its eigenvalues were 3 and negative 1. Its eigenvectors were 1, 1 and negative 1, 1. That means A to the power n is P d to the n P inverse. That's 1, negative 1, 1, 1 times 3 to the n 0, 0, negative 1 to the n times the inverse of P. Inverse of a 2 by 2 is very easy. You use that formula, 1 over the determinant, that's 1 over 2. Flip the two diagonal entries and change the sign of the off-diagonal entries, multiply out, and I get this formula for A to the power n. And I can check it by just plugging in n equals 2. That gives me 5, 4, 4, 5, which you can confirm is in fact the matrix A squared, or A times A. Let's just wrap up today by having a look at MATLAB Octave. Here I am in Octave and seeing how to diagonalize a matrix using MATLAB or Octave. Let's take A equals, I'll just do the matrix I had before, 1, 2, 2, 1. So the command for eigenvalues is eig. There are the eigenvalues, negative 1 and 3. They are returned as a vector. If you want to have the eigenvalues as well, you need to give two output arguments. First a matrix of eigenvectors, and then a matrix of eigenvalues. And that returns two things. And notice that the eigenvectors form the columns of the matrix P. Now, when I did this by hand, for the eigenvalue minus 1, I got eigenvector minus 1, 1. Here it's minus 1 over root 2, 1 over root 2. They've just normalized that by taking that vector and dividing by its length. So MATLAB will return the eigenvectors as unit vectors. For the eigenvalue 3, I've got the eigenvector 1, 1, or a scalar multiple of it, namely 1 over root 2, 1 over root 2. So this matrix should diagonalize A, so let's check the inverse of P times A times P. And you see here I've got the 1 times 10 to the minus 17. That's basically 0. That's just a small floating point error there. The diagonal entries are minus 1, 3. Let's take a bigger matrix. So I had 2, 0, 3, 2, 0, 3, 3, 2, 0. PD equals eiga. The eigenvalues, notice that there's no natural order in which to return the eigenvalues. Here the eigenvalues are 5, 0, basically a very small number close to 0, negative 3. The eigenvectors have been returned as unit vectors. This was the one that I calculated by hand to be 1, 1, 1. Here it's been multiplied by minus 1 over root 3, just a scalar multiple of it. Again, inverse of P times A times P should be a diagonal matrix. The great advantage, of course, is that I can now calculate eigenvalues of very large matrices. So let's take a random 8 by 8 matrix. Can't even see the whole thing on the screen there. What are its eigenvalues? Notice that some of them are real and some are complex. I've got real, 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 complex conjugate pair, and another real one. So this matrix, it has 8 eigenvalues, 4 are real, and 4 are formed into 2 complex conjugate pairs. You can calculate the eigenvalues and eigenvectors of very large matrices indeed. Let's do A equals rand 1000. So that's a 1000 by 1000 matrix with 1 million entries. That didn't take long to compute. Now I will compute its eigenvectors V. I'll put a semicolon because I don't actually want to see the eigenvalues. How long does that take? It's computing. It's done. Took a couple of seconds on my laptop. Now, in an engineering application, for example, if you had an engineering structure with a few thousand parts, that's going to be a large matrix, a few thousand rows and columns, where the entries give the strength of the linkage between the different parts. The eigenvalues will tell you the natural modes of response of that structure when it's subject to a force. For example, does it oscillate? What frequencies does it oscillate at? How rapidly do those oscillations decay? So the eigenvalues will tell you a lot about the structure of a matrix, much more than just the list of a million numbers, which are impossible to make sense of. Likewise in statistics, when you have a large matrix, you've got collected a lot of data, say 100 observations, 100 different things about thousands of different people. The eigenvalues will let you pull out the relevant or main factors out of that data.